Alrighty. Should I go ahead and start then?
Go ahead.
Perfect. Alrighty, so my name is Gordy Driver. I am one of the science presenters here at the museum. I work under the Science and Nature Coordinator, so I am one of the people that helps make one of these awesome galleries possible for you guys to visit today. So today we'll be doing a show that I like to call Super Cold Science. I'll be working with super cold liquids to be able to cause chemical reactions to occur right in front of your eyes. You may see things that might be stuff that you've never seen before. You may have seen things that you've seen all the time, but you didn't realize actually existed in our everyday life. I'm going to be showing you a few of those things today. I'm going to be explaining what exactly those things are. But first and foremost, in every single science show, it's always important to be wearing safety or take safety precautions. So for the duration of the show, I'd like to kindly ask that you remain behind this stanchion border that I have put right behind here for your guys' safety as well as my own. So just so I can keep a nice room available to be able to conduct these experiments. As you can see, I am wearing a face shield in front of me, which allows me not to wear a face mask. I like doing these kinds of shows because I can get away with this kind of stuff, and the FBI doesn't have to hunt me down for not following their restrictions. But regardless, I also have these very fancy gloves on my hands. They're kind of bluish. They're actually called Cryogloves. These are intended to keep my hands very, very warm under very cold temperatures, very similar to snow gloves if you ever go to Mount Charleston or to Big Bear or anywhere where it might be nice and frosty. So I've also got this lab coat that I'm wearing today in case there's any splashing of chemicals that I'll be using. I don't get on myself, I don't hurt myself, but at the same time I also am doing it just for being safe. All the chemicals I'll be working with today are actually going to be safe to breathe. So even though we have this very nice fume hood that we can use for all of our experimentations, we will not be needing it today. I believe Sam Nelson told you what kind of liquid we're working with today. Does anybody know what kind of liquid we're working with today? By raise their hand. Yes. Liquid nitrogen. Very good. So nitrogen actually exists very naturally in our atmosphere. We're breathing it actually right now. Up to 80% of our atmosphere is liquid, nitrogen gas, meaning that the other 20% is
Oxygen.
oxygen. Very good. So it's stuff we breathe every single day. Very good. So I'm going to go ahead and I'll show you what we'll be working with right now. So this is what we call a scientific dewar. So a scientific dewar is simply just a flask that you might imagine. Breathing. It's always good to do, especially for presentations. Yes. So scientific flask. Imagine that this would be what's a great comparison? A thermos. So who here has ever owned a thermos before? I know exactly what a thermos is. Very good, very good. So a thermos, it keeps things hot and the cold things cold. You use for a cold drink on a hot day or a hot drink on a cold day. So this is what we call a scientific dewar. It's basically a scientific thermos. This has the capacity of keeping things at extreme temperatures. So either very extremely hot, like molten lava, or things that are extremely cold, like liquid nitrogen. How cold are we talking about? Well, let's do a little experiment here real quick. Everybody go ahead and raise your hand, one of your hands, any available hand that you have real quick. I want you to go ahead and I want you to drop that hand when we've reached the coldest temperature you've ever experienced. So let's start it easy. Let's go with 100 degrees. Good, we live in Las Vegas, Nevada. Everybody's hands should be up. Let's go ahead and go to 90 degrees. 80 degrees. Good, it was 80 degrees today. 70 degrees. 60 degrees. 50 degrees. Good. 40 degrees. 30 degrees. 20 degrees Fahrenheit. Okay. Saw one hand drop. 10 degrees Fahrenheit. Some more hands. 0 degrees Fahrenheit. Alrighty. Negative 10 degrees Fahrenheit.
Okay, Miss North Dakota.
Negative 20 degrees Fahrenheit. Negative 30 degrees Fahrenheit. Alright. What's the coldest you've experienced?
68 degrees.
68 degrees. Negative 68? Okay, negative 68. Where was that? North Dakota? Very, very nice. I myself am from Toronto, Canada, so I understand cold weather very well. So, surprisingly enough, you might think that this might be at a nice frosty negative 68 degrees Fahrenheit. Ladies and gentlemen, this is sitting at a nice frosty negative 321 degrees Fahrenheit in my hands right now. Can we survive at temperatures at negative 321 degrees? No. Do you think liquid nitrogen exists naturally here on Earth? Raise your hand if you think yes. Raise your hand if you think no. You'd be smart to say no. The only place that we have actually discovered Liquid nitrogen naturally in our galaxy, or rather in this case in our solar system, would be Pluto. Pluto is known to have oceans of liquid nitrogen.
Wow.
In fact, it's said by NASA scientists that we have discovered oceans of liquid nitrogen with glaciers sitting on top on Pluto, which is fascinating to think about. But you guys have only heard of nitrogen gas before, so let's go ahead and take a quick look at what liquid nitrogen actually appears. And I've got this very nice styrofoam box right here that is a great insulator. If you guys don't know what an insulator is, it just means that it retains temperature pretty well. It doesn't absorb temperature, it keeps temperature where it should be. Let's go ahead and take a look what this looks like. So I'm going to go ahead and pour this out. And I want you to tell me, does it run smooth like water or does it run slow like honey? On the count of 3, ready? 1, 2, 3. Like water, exactly. And funny enough, you wouldn't think that something this cold, negative 321 degrees, flows very much like water. Go ahead and pour that for you one more time. I'm actually going to go ahead and pour this a little bit on the floor. I want you to go ahead and make the observation that you see when I pour some of this onto the floor. On the count of 3, once again. Ready? 1, 2, 3. Now, did it leave a puddle at all?
No.
No. That's because it has a boiling point at that negative 321 degrees Fahrenheit. Or exactly, if we were to say conversely, that it evaporates at negative 321 degrees. What's the temperature here? What would you guess?
72.
About 72 degrees. It's a good temperature. So that,
72, sure.
so that's about a 400-degree difference. So imagine we were pouring water on boiling lava. And that's basically what I did with liquid nitrogen just now, because that's how fast it evaporated. So let's go ahead and let's take a closer look at what liquid nitrogen actually looks like. So I went ahead and poured some of this. By the way, all these things that are coming out, what would you call that?
Steam.
Some would call it steam.
Smoke.
It's not exactly smoke, I'm not burning anything. Fog would be a great answer, because we have water molecules that naturally occur all across our atmosphere. And the cold temperature, the negative 321 degrees Fahrenheit, is condensing all those water molecules instantaneously, creating a layer of fog over our liquid nitrogen. So let's go ahead and take a look at what it looks like. As you might imagine, it probably looks something like boiling water. Now, you can't hear anything, but you can definitely see it. It's boiling right now. And so what this is doing is it's creating a whole bunch of nitrogen gas as it's moving along. And as you can see, as I hold it in front of you, you're going to see the bottom of it frost right in front of your eyes, because those water molecules are going to freeze along the outside of my flask right here. And now I'm going to go ahead. I'm going to pour it into this nice little triangular flask right here. And we're going to see how much gas is this actually producing. Now you can hear stuff, because the outside is frosting over. I'm going to go ahead and pour this in. And I've got this very nice little top, this little stopper right here that actually goes right on top, and it's got a little balloon. We're going to see how much gas it produces. Ready? On the count of 3. 1, 2, 3. And it's going to continue going. So I intentionally let some of the nitrogen gas out. And once again, if I were to pop this, would it be okay to breathe? Yes, it would be very much okay to breathe. I'm going to go ahead and tie this balloon. I'm taking my gloves off very quickly. Do you think this is super cold that's sitting inside here? It's kind of cold. It's not exactly cold. Once it evaporates, it gets to a very nice 30 degrees Fahrenheit pretty quickly. It's not entirely biting for my hands. It's cold, but it's not biting. And I'm going to go ahead. I'm going to take my balloon. We're going to go ahead. I'll tie your balloons with me. Here we go. And drop it right in our liquid nitrogen. And some of you are thinking, it's going to pop. I'm here to tell you today that you may or may not have a fear of popping for this one. So now it is making noise. What is that sound? What does it sound like?
Sloshing.
Sounds like ice. I don't know, it kind of sounds like a tin foil almost.
Oh, wow.
Maybe a plastic bag from a grocery store. So now that's saturated in there. I'm actually going to let it sit in there just for a little bit longer. We're going to do a quick demonstration. So whenever I teach science, I used to be a mathematics teacher at a private school before I started this job. And I used to teach a little bit of science as well as a TA at my college. So before I teach any science or math, I like to probe the crowd or whoever I'm teaching with some scientific terms and see what they know. Raise your hand if you've heard the term states of matter. Oh, very good. Raise your hand if you've heard the term thermodynamics. Very good. Okay. So I will go ahead and explain this to you, for those of you who have not raised your hands, in a way that's simplified. So everything around us is made of atoms. Everything's made of molecules, correct? So we were talking about water molecules in the air. We breathe oxygen molecules. And those molecules are made of smaller atoms that exist in everything that is. So it's all matter, air, breathe, air, breathe. All right, presentations. So everything is made of these particles. And particles have the ability to change states of rhythm based on how fast it is. So go ahead and take your hands, put them into a fist like this. This is how I like to teach the kids. So when you put your hands like this, you can kind of move them just very, very subtly. This is how we represent molecules that are in a solid. So when we're talking about stone, ice, metal, these are molecules that are moving very, very slowly and very close to each other. That's why they have so much resistance. Now if we add a little bit of heat, depending on what the substance is, the molecules will start to vibrate faster. And they'll start to dance around a little bit more. And these are what molecules look like when it's in the form of a liquid. They can move around freely. They can be a little more vascular. They can move without constraint, or not as much constraint. And then you add a lot more heat. And if you want to, I always tell the kids, don't punch your neighbor. But this is what gas molecules look like. And the gas molecules get really excited and they can move in massive quantities. Bernoulli's principle says that PV equals nRT. That stands for pressure and volume is equal to the molar mass times, goodness, some really scientific guy's number times temperature. That means that pressure is relative to temperature. That means things can change, can expand, or get really small based on temperature. Usually, when we're talking about temperatures, especially significantly cold temperatures, things are bound to get very small.
Oh, wow.
And as you see, the balloon, as it's readjusting to the temperature that's in our room, is going to expand naturally. And what we've got right here, the outside is just a little bit cold, is your ordinary balloon. You can see at the bottom, it's the frosting from that liquid nitrogen. And we've got a perfectly ordinary balloon. Now it's going to continue to expand a little bit, and may have been pop since I left it in there for so long. But we're going to go ahead and take another example and see microphones. Check 1, 2, can you hear me? Check 1, 2, can you hear me again? All right. So
It's the balloon.
check 1, 2. Going back to the, you left me in for too long. I'm gonna find you now. So now we're going to do a quick experiment. So let's talk about maybe everyday home life. So if you have done some cooking in your house, you should know a general rule is to never put something super hot under something super cold. So say you've got a baking pan that you've left in there, it's made out of acrylic or Pyrex, and you leave it under in a hot oven that bakes around 300 degrees Fahrenheit, and you suddenly decide, oh, I gotta take my dish out of the oven, I gotta stick it under water and cool it off because I gotta get the next dish. And you put it under, and what happens usually? Cracks, breaks, pops. Because those molecules that we're talking about quickly contract to the point that the glass can't handle it, and you've got broken dishware. So what that tells us is that extreme temperatures don't usually like to interact as well. So today, we're going to be conducting an experiment where we see a cloud form right before our very eyes. And when I say a cloud, I mean an actual cloud that you see in the sky. So like I told you before, water molecules exist all around us, and they can be harnessed by simply turning on a tap water and pouring it into something very simple as, I don't know, a boiling kettle right here. So what we're going to do is I preheated this water. This is sitting at a nice, does anybody know what the boiling temperature water is? Just a quick guess. Little trivia question. What was it? 212 degrees Fahrenheit. Very good. So this water is sitting at just below 212 degrees Fahrenheit. And I'm going to have a very fun time pouring this hot water into this flask. And then we're going to pour this flask directly into our liquid nitrogen. Are you guys ready to see a fun little experiment today?
All right. Check 1, 2. Is it coming out anymore? Can you hear me? Nope. So I'm just projecting right now. You can hear me just fine?
Yeah, we hear you.
Perfect. All right. So ladies and gentlemen, what's going to happen is I'm going to go ahead and pour this nice hot water right here, and you can actually see it starting to steam outside on the sides. I'm going to pour it right in here, and you're going to see an explosion that happens right in front of your eyes. The reaction will occur so quick that you might not be able to tell. Or maybe you will. I mean, what I usually like to do during a show, especially for kids, I like to envision this like a gladiator match. Water versus liquid nitrogen. Your famous using for tea versus something strange and ordinary from the planet Pluto. Who do you think is going to win? Raise your hand if you think water's going to win today. Water will win if you've got frozen ice, or if you've got water just sitting at the end. Liquid nitrogen will win if you've got solid ice. Raise your hand if you think water's going to win today, ladies and gentlemen. Come on, cast your votes. This is Las Vegas. Raise your hand if you think water's going to win. Nobody thinks water's going to win. Wow. Okay. Who thinks the liquid nitrogen's going to win? Alrighty. Ladies and gentlemen, let's go ahead and make that collab now. On the count of 3, ready? 1, 2, 3.
Whoa.
We call
And if you
that
stick your
dancing
hands
on
down by the
clouds.
cloud that maybe or may not be reaching towards you, you can feel a very, very drastic temperature difference. I'm going to go ahead and take this off because it's not doing me any help. And I'll bring this over to you guys. You can actually feel the cold temperature difference by bringing it towards you.
Like home.
Now you might be thinking, Mr. Gordy, you don't have your gloves on. It is not considered that cold. The temperature difference has already changed quite drastically, so my hands are perfectly fine.
Chilly.
If you feel that, even that condensation that's pouring out right now, you can feel the cold. And all it is. In fact, this condensation, this fog that's forming right now is so heavy, I can pour it out like water. Very, very cool.
They use them, you know, they use them on a lot of special events.
What was that?
We use them a lot on special events.
Liquid
Clients,
nitrogen?
when clients want to dance on the clouds, they
Oh.
call it dancing in the clouds.
Very nice. So you just use liquid nitrogen.
Well, there's a machine.
Ah, I see.
Yeah.
So foggers. Yes.
No, it's not fun.
Not foggers. It is liquid nitrogen.
Yeah.
That's fascinating. That's very, very fascinating. Well, liquid nitrogen is actually used every day in our lives, and you may not even realize it. So what might be a good application for liquid nitrogen? Does anybody know? What do you have in your households all the time that keeps the stuff cold? Refrigerators and refrigerators. Liquid nitrogen, everybody. So let's go ahead and I'll pull some of this out for you guys to see today. Hold it. We can try and drink it. Not effective, unfortunately. So let's go ahead and see who won. Did the liquid nitrogen win? Because I'm hearing that crackling's finishing up. By the way, that crackling was the formation of ice crystals instantaneously forming. And remember, this was boiling water we worked with at the beginning. And now it is possibly even frozen ice. So let's go ahead. Let's see what the result is. I'm going to go ahead and pour this out. Looks like water is our victor for now. But even then, with this water, you can see at the bottom that there's a formation of pure. I'm so sorry. I'm not even serious. With pure ice sitting at the bottom, which is our boiling water that once was there.
Everybody's a winner.
Ladies and gentlemen, this has been my production of Super Cold Science. I hope you learned. I'll go ahead.